In 1916, a German physicist named Karl Schwarzschild solved Einstein's equations from a hospital bed on the Russian front, and buried inside his own solution was a second object nobody had asked for. It would take another 44 years for anyone to find it. Run the mathematics of a black hole backward in time, and the equations don't break. They describe something that only ever pushes matter out and can never let anything in. Not light, not a falling stone, nothing. A black hole's horizon is a door that only opens inward. This object's horizon is the same door, facing the other way. Astronomers have pointed instruments at the sky since the 1960s looking for one. Not a single confirmed white hole has ever been found, and the reason turns out to have nothing to do with how rare they might be. It has to do with how quickly one would die. Karl Schwarzschild was over 40 when the First World War started, old enough that nobody would have blamed him for staying home. He volunteered anyway, and by the end of 1915 he was serving with the German artillery on the Eastern Front, calculating trajectories for guns instead of stars. That December, a copy of Einstein's new paper on general relativity reached him in the field. Einstein had only managed an approximate solution to his own equations, admitting as much in the paper itself. The full equations were considered too difficult to solve exactly. Schwarzschild disagreed, or at least wanted to see for himself. Between artillery positions, in a letter dated the 22nd of December, he wrote to Einstein that the war had been kindly disposed toward him, allowing him this walk through Einstein's ideas despite the gunfire. He had found an exact solution, not an approximation, the precise geometry of space-time around a single spherical mass, worked out with pencil and paper somewhere near the front line. Einstein wrote back the following month. He said he had not expected the exact solution to a problem this hard to come out so simply. That is a striking thing for the man who invented the theory to say about someone else's solution to it, and it says something about how clean Schwarzschild's answer really was. Schwarzschild did not get long to enjoy it. Not long after, he contracted a rare autoimmune skin disease while still in Russia. He was sent home in March of 1916. He died on the 11th of May, 2 months later, at 42 years old. He had perhaps 4 months total between finding the solution and losing his life to a disease with no treatment available at the time. Here is the part that took me a while to sit with properly. Schwarzschild's solution contains two mathematical features that don't behave the way normal geometry behaves. One sits at the very center, where the equations produce infinite density, a true singularity. The other sits at a specific distance from that center, a radius now called the Schwarzschild radius, where something odd happens to the mathematics without anything physically dramatic seeming to occur there. For decades, nobody was sure what to make of that second feature. Schwarzschild himself seems to have treated it as a mathematical curiosity, not a place with physical consequences. The horizon, as we'd now call it, was widely treated as an artifact of the coordinate system Schwarzschild happened to choose. A flaw in the map, not a feature of the territory. The first real crack in that view came in 1933, when the Belgian physicist and priest Georges Lemaitre showed that if you simply chose different coordinates to describe the same physical situation, the strange behavior at that radius disappeared entirely. The singularity at the center stayed. The one at the horizon vanished. That was the first hint that the horizon was not a breakdown of physics, but a limitation of how one particular observer, sitting far away, was choosing to describe it. The scientific community did not settle quickly. In 1939, two competing papers reached opposite conclusions within months of each other. Einstein published one of them, arguing that nature would simply never allow matter to compress down that far in the first place, that some physical process would always intervene before a star could reach its own horizon. He was defending the older view that the horizon was not a place a real object could ever actually arrive at. The second 1939 paper disagreed, and it came from Robert Oppenheimer, 7 years before Los Alamos, working with a graduate student named Hartland Snyder. They modeled what would actually happen if a massive enough star ran out of fuel and began to collapse under its own weight, with nothing left to hold it up. Their mathematics found that the collapse would not stop and would not need any exotic new physics to keep going. From the outside, an observer watching it happen would see the star appear to freeze at the edge of that same critical radius, its light stretching and dimming toward nothing, seemingly suspended there forever. But for anyone falling inward with the star itself, nothing would feel frozen at all. They would cross that boundary in a perfectly ordinary, finite amount of time, and keep falling, feeling nothing unusual at the crossing itself. Two physicists the same year, looking at the same equations and reaching opposite verdicts about whether the horizon was a place anything could actually reach. Oppenheimer and Snyder's version is the one later observation would side with. But it took the wider field years to treat their result as more than a mathematical exercise, partly because the Second World War scattered the community that might have argued it out, and partly because Oppenheimer himself moved on to other work not long after. What strikes me is the gap in all of this. Schwarzschild wrote down the complete solution in 1916. Lemaitre showed the horizon wasn't what everyone assumed it was in 1933. Oppenheimer and Snyder showed what falling through one would actually look like, from both sides of it, in 1939. And the full picture of what that original solution actually contained, the entire structure hiding inside those equations, still would not be understood for another 2 decades after that. An exact answer sat on paper for over 40 years before anyone had drawn the whole map of what it described. Not because the mathematics was wrong, because nobody had yet asked the question in a way that forced the rest of the picture into view. If you found your way to this channel before and know how these nights tend to go, you already know we're not in a hurry to get anywhere. If this is your first time here, welcome. Either way, if a slow, honest walk through something this strange is the kind of company you're after at this hour, staying subscribed means you'll have more of these to fall asleep to. That's the only mention I'll make of it. The rest of that picture, the part hiding just past the horizon, is where this gets stranger. Because when physicists finally did draw the complete map of Schwarzschild's geometry in full, they found something on it that nobody had gone looking for at all. For those first decades, everyone working with Schwarzschild's solution was really only looking at half of it. They had the region outside the horizon, where we live, where light and stars and planets behave the way you'd expect. They had the singularity at the center. What they didn't have, because nobody had gone looking for it, was a complete picture of what the mathematics permitted beyond that boundary. That changed in 1960, and it changed twice, independently, within months, by two people who weren't working together at all. Martin Kruskal was an American physicist at Princeton, mostly known at the time for his work on plasma physics, something that had nothing to do with black holes. George Zakaries was a Hungarian-Australian mathematician who had survived the Holocaust and later built a career in pure mathematics at the University of Adelaide. Neither man set out to discover a new region of space-time. Both arrived at the same coordinate system almost by accident, while trying to clean up the mathematics of the Schwarzschild solution so it behaved better near the horizon. What they found, when the coordinates were finally right, is that Schwarzschild's solution doesn't describe two regions. It describes four. The first is the one you'd expect, our universe, on the outside, at a safe distance from the horizon. The second is the black hole interior, the region you can fall into but never leave, ending at the central singularity. So far, nothing surprising, but the mathematics didn't stop there. A third region appeared, structurally identical to the black hole interior, but with time running the other way through it. A region nothing can enter, and everything inside is compelled to leave. That's the white hole. And a fourth region appeared alongside it, a second exterior universe, causally disconnected from our own, connected to us only through a bridge that pinches shut too quickly for anything to actually cross it. Physicists sometimes call that bridge an Einstein-Rosen bridge, the same mathematical object that gets casually called a wormhole in less careful conversations, though this particular version was never traversable by anything. There's a detail about how this got published that I like more than I probably should. Karl worked out the full coordinate transformation, but by his own account, he didn't think it was significant enough to write up properly himself. It was John Wheeler, the physicist who later coined the term black hole, who recognized what Karl had found and pushed to get it into print. Wheeler is often credited with having essentially written the paper's presentation from Karl's results, reportedly starting from calculations Karl had sketched out casually rather than as a finished argument. The version of events differs depending on which account you read, but the shape of it holds. The person who found the complete structure of space-time around a black hole almost didn't think it was worth telling anyone about. In human terms, what this means is that the same set of equations describing a black hole, if you extend them as far as they mathematically go, don't just describe one strange object, they describe two, glued together at a boundary neither one can cross, sitting inside a diagram with two separate universes that can never speak to each other. Nobody built this into the theory on purpose. It was already there, in 1916, waiting for someone to draw the coordinates correctly enough to see it. It's worth being precise about what the white hole region actually is, because it's easy to round it off into a black hole in reverse and lose what makes it strange. It is not a different kind of object sitting somewhere else in the universe. In the Kruskal-Shekera's diagram, it shares the exact same mass, the exact same horizon radius, the exact same exterior geometry as the black hole region beside it. The only difference is the direction of the boundary's one-way permission. A black hole's horizon lets things cross inward and never back out. A white hole's horizon, the mathematics says, lets things cross outward and never back in. Everything about its structure is inherited from the black hole. Only the arrow is flipped. This is also where the picture gets its first real complication, one worth sitting with before going further. The white hole region in the Kruskal diagram isn't formed by anything. It doesn't have a birth the way a black hole does, collapsing from a dying star at some particular moment in cosmic history. In the pure mathematical solution, it has simply always existed, stretching infinitely into the past, the same way the black hole region stretches infinitely into the future. That's a mathematical idealization, and it's one of the first cracks in the idea that a white hole could be a real, physical object rather than a permanent feature of an eternal, unchanging space-time that nothing in the real universe actually is. For a long time, That was where the textbooks mostly left it. An elegant, complete structure. 4 regions in one diagram, mathematically airtight, and almost certainly not describing anything that has ever existed. A curiosity in general relativity courses, filed next to other honest mathematical results that don't seem to correspond to anything nature actually built. But an idealization is not the same thing as a dead end. If a real black hole could ever be pushed toward behaving even a little like this eternal, idealized one, even briefly, even incompletely, the question of whether something white hole-shaped might exist doesn't go away. It just changes what has to be asked. Not, does this exact eternal object exist? But, can anything real ever come close enough to it to matter? To answer that, you have to stop treating the white hole as a fixed diagram and start treating it as a physical process, something that would have to begin, behave, and very possibly end the way anything real does. Think about a film of a diver falling from a board into a pool. Play it forward, and it looks like what it is: a body leaving the air, breaking the surface, water closing over it. Play the same film backward, and something else happens. The water pulls itself apart, gathers around a shape, and lifts a diver cleanly up onto the board, dry, standing as if none of it happened. Nothing about the backward version breaks any law of motion. Every frame still obeys the same physics, run the other way. It simply looks impossible, because in this universe, water does not spontaneously organize itself into throwing people into the air. That's the cleanest way I know to hold on to what a white hole actually is. The equations of general relativity in their basic vacuum form don't have a built-in arrow of time. If a particular solution describes a valid way for space-time to behave, running that same solution backward through time is, mathematically, just as valid. A black hole is one direction of the Schwarzschild solution. A white hole is the same solution, the same mass, the same geometry, played the other way. What changes is not the shape of the horizon, it's the permission at the boundary. A black hole's horizon allows motion in one direction only, inward. Once you cross it, every possible path forward in time leads deeper in, toward the singularity, with no path back out, not for light, not for anything. A white hole's horizon allows motion in exactly the opposite single direction, outward only. Nothing, no matter how it approaches, no matter how fast, no matter from how far away, can cross a white hole's horizon going in. The boundary simply doesn't have an inward-facing door. It only has an exit. This is worth being precise about, because it's easy to imagine a white hole as something you could still fall into if you got unlucky. Just a strange place once you're inside. That isn't what the mathematics says. Gravity still pulls on a white hole. It still has mass, and mass still curves space-time. And a distant object would still feel an ordinary gravitational tug toward it, the same as toward any other object of that mass. What's different is what happens as you get close. As you approach the horizon, the geometry itself won't let the crossing complete. You can fall toward a white hole. You cannot fall into one. The two verbs describe completely different situations here, and the horizon is the reason. For context, it helps to think about what can't means in this specific case. It isn't cannot the way you cannot walk through a wall where some force resists you. It's closer to cannot the way you cannot arrive at yesterday. The horizon of a white hole isn't a barrier standing in your way. It's a boundary in time itself, and asking to cross it inward is structurally the same kind of request as asking to travel into your own past. The mathematics doesn't forbid it with a wall. It forbids it the way causality forbids effects from preceding their causes. That comparison points at the deepest problem with treating a white hole as something that could simply exist out there, waiting to be found. A black hole has an origin story that makes sense within ordinary time. A star runs out of fuel. Gravity wins. The star collapses past its own horizon, and a black hole is born at that moment. An event with a location and a date, at least in principle. A white hole, in its pure mathematical form, has no such moment. Everything that will ever emerge from it is already fixed by what's called a past singularity, a starting condition sitting at the very beginning of that region's existence, one that nothing inside the observable universe caused or chose. It doesn't come into being the way a black hole does. In the clean, idealized mathematics, it has simply always been there, since before there was a before for it to arrive after. I remember finding this the hardest part to actually accept, not because the mathematics was unclear, but because everything else in physics I'd ever been taught has a cause coming before its effect. And this is a case where the effect, in a sense, doesn't have one within reach at all. Physicists sometimes describe this as a white hole requiring an initial condition rather than a cause, which sounds like a technical distinction until you sit with what it actually means. The entire future of that region of space-time was decided by something outside of time, as we experience it, not by any event you could point to. None of this makes the mathematics wrong. The equations are entirely self-consistent. A white hole is not a contradiction, the way a shape with 5 right angles in flat geometry would be a contradiction. It's a legitimate solution to a real physical theory that has been tested to extraordinary precision in every other regime we've managed to check it in. What it means is that a white hole, taken as this eternal, uncaused object, was never going to be something you could point a telescope at and expect to catch in the act of forming, the way we've caught black holes forming from collapsing stars. If a white hole was ever going to matter to the real, physical universe, it was going to need a different story than the one sitting in Schwarzschild's original, idealized solution. That different story is where the actual search begins, and it starts by asking a much more grounded question than any of this. If you built something white hole shaped out of ordinary matter, rather than assuming it into existence as a mathematical boundary condition, how long would it actually last? By the early 1970s, the mathematics of white holes was well understood, and the observational record was exactly what it had always been. Nothing. No confirmed detection, no candidate that had survived scrutiny. Decades of instruments finding nothing that could be pinned to this specific idea. The usual explanation at the time was the same one you'd reach for with almost anything unseen in astronomy. Maybe they're rare, maybe they're far away, maybe our instruments simply aren't good enough yet. In 1974, a physicist named Douglas Eardley, then at Caltech, published a short paper in Physical Review Letters that offered a very different explanation, and a far less comfortable one. His paper was called Death of White Holes in the Early Universe, and the title says almost everything you need to know about the conclusion before reading a word of the argument. Eardley wasn't asking whether white holes were rare. He was asking what would happen to one the moment it stopped being alone in an empty universe, and the answer he found was that it would not survive contact with anything at all. The mechanism is worth walking through slowly because it isn't intuitive at first. A white hole's horizon only allows matter to leave. But a horizon is still a place, still sitting in a universe with other things in it, and other things, however sparse, will occasionally drift close to it. even a wisp of gas, even a few stray photons of ambient light. When that matter approaches the horizon from outside, it doesn't cross in because nothing can, but it doesn't simply bounce away either. According to Erdely's calculation, that infalling material undergoes an extreme blue shift as it nears the boundary, its energy compressing and intensifying the closer it gets, piling up right at the edge of the horizon rather than passing through it. That pile-up doesn't stay small. The build-up of blue-shifted energy right at the boundary is, by the equations of general relativity, itself a source of gravity, and a large enough concentration of energy in a small enough region does exactly what concentrated energy always does in this theory. It curves space-time sharply enough to collapse the geometry. Erdely's calculation showed that this collapse happens almost immediately, converting the white hole into an ordinary black hole before any substantial amount of matter ever gets close to it. Not eventually, not after some long astronomical process. The instability triggers on contact with essentially any external matter, however small. In human terms, this means the horizon that is supposed to let nothing in turns out to have an Achilles heel built directly into that same restriction. It can refuse entry to everything, and that refusal is exactly what dooms it, because refused matter has nowhere to go but into a pile that eventually crushes the very geometry doing the refusing. I remember the specific disappointment of reading Erdely's result properly for the first time. This is one of the more elegant structures in general relativity. A clean, complete, mathematically airtight object, sitting right there in Schwarzschild's original solution since 1916. And the thing that ends it isn't some competing theory or some later revision to the physics. It's the plainest possible fact about any real universe that there is always something else nearby. A single atom drifting past is enough, given enough time, to unmake it. The consequence of this is stark, and it's worth stating directly. An eternal, stable white hole, the kind sitting in the pure Kruskal-Seeker's diagram, can only exist in a space-time containing absolutely nothing else. No gas, no light, no dust, no other mass anywhere nearby. Later refinements to Erdely's original calculation, notably by Karl and Roy Roeder, later in the 1970s, and by Stephen Blau afterward, adjusted some of the details of exactly how fast the collapse proceeds under different assumptions. None of these refinements rescued the underlying conclusion. The white hole, once it meets any external matter at all, stops being a white hole. If you're still with me at this point in the night, here's the plain version of why this matters to the question we actually started with. We have never confirmed a single observation of a white hole, and the instinct is to blame the search. Wrong instruments, wrong wavelengths, wrong place to look. Erdely's result suggests something closer to the opposite. It isn't that we haven't looked well enough, it's that the object being searched for may be structurally incapable of lasting long enough, anywhere in a real, populated universe, to be caught in the act. Our universe, at every point in its history, since the earliest fractions of a second, has been full of something. Plasma, gas, radiation, dust, structure. There has never been a truly empty patch of space-time for an eternal white hole to sit in, undisturbed. That leaves the idea in a strange position. Not disproven, exactly. The mathematics inside Schwarzschild's solution is still there, still self-consistent, still a valid answer to Einstein's equations. But cornered badly by the plain fact that the universe we actually live in has never once been empty enough to let that answer survive contact with it. Which raises the obvious next question, the one that would occupy physicists for another 40 years after Erdely's paper. If a classical white hole cannot last in a real universe, is that the end of the story? Or is there a version of this idea that doesn't require starting from nothing? Erdely's result held for 40 years without serious challenge, and for good reason. It was built entirely on general relativity, the same theory that predicts the white hole in the first place. And within that theory, the conclusion is hard to escape. But general relativity is not the final word on gravity. It breaks down at the smallest scales, right around a singularity, which is precisely where any honest discussion of white holes eventually has to go. And it was exactly there, at that breakdown, that a small group of physicists found a way to ask the question again. The key figure here is Carlo Rovelli, an Italian theoretical physicist and one of the founders of an approach called loop quantum gravity, which attempts to describe space-time itself as built from discrete, quantized pieces rather than the smooth, continuous fabric general relativity assumes. In 2014, Rovelli and a colleague named Francesca Vidotto published a paper proposing something they called a Planck star. Their idea was that gravitational collapse, the same process that forms an ordinary black hole, would not actually continue all the way down to a true singularity of infinite density. Instead, once the collapsing matter reached a specific, extremely high density called the Planck density, roughly the density at which quantum gravitational effects become unavoidable, the collapse would simply stop. Quantum pressure, rather than any classical force, would halt it. That alone is a significant claim, since it removes the singularity from the center of a black hole entirely, replacing infinite density with an enormously dense but finite core. But Rovelli, working the following year with Hal Haggard, took the idea one step further. If the collapse halts rather than continuing forever, what happens next? Their answer, published in 2014 and expanded in 2015, was that the collapsed matter could tunnel, in the quantum mechanical sense, from the black hole configuration into a white hole configuration, not colliding with anything from outside, the way Erdely's instability requires. Bouncing from the inside on its own. The most useful anchor for holding onto this is a ball thrown straight into the air. Classically, in the moment before it starts to fall back down, the ball's motion looks continuous, smooth, one single arc. But imagine instead that going up and coming down were two distinct physical states, and that at the peak, rather than smoothly transitioning between them, the ball had some genuine quantum probability of tunneling directly from the going up state into the coming down state, skipping the classical transition altogether. That's structurally close to what Haggard and Rovelli are proposing for a collapsing star. The black hole phase and the white hole phase are two configurations of the same physical system, and quantum mechanics allows a transition between them that classical general relativity on its own does not. This doesn't sidestep Erdely's argument. It answers a different question than Erdely asked. Erdely showed that an eternal, pre-existing white hole cannot survive contact with ordinary matter. Haggard and Rovelli are not proposing an eternal white hole. They're proposing a brief, transient one, a black hole that collapses, halts at the Planck density, and bounces back outward as a white hole phase, all within a finite lifetime, rather than sitting there forever waiting to be destabilized. The object this describes wouldn't need emptiness to survive, because it isn't trying to last. It's trying to happen once, briefly, and then be done. If this bounce happens at all, it would need to leave some kind of trace, and this is where the proposal becomes something you could, in principle, actually go looking for. In 2014, working with Aurélien Barraud, Rovelli and Vidotto suggested that the sudden release of energy from a black hole completing this bounce, particularly a primordial black hole, one formed in the extremely early universe, rather than from a collapsing star, could produce a short, sharp burst of radio waves. Their proposed signature bears some resemblance to fast radio bursts, a real and well-documented class of millisecond duration radio flashes that astronomers have been cataloguing since 2007. I want to be precise here, because it would be easy to overstate this. Fast radio bursts are real, confirmed, extensively observed phenomena. The overwhelming majority of them have conventional explanations involving magnetars, highly magnetized neutron stars, and that explanation is well supported by direct observational evidence, including at least one fast radio burst traced to a magnetar inside our own galaxy in 2020. No fast radio burst has been confirmed to originate from a black hole to white hole bounce. The proposal remains a theoretical suggestion sitting inside an unproven framework of quantum gravity, one candidate explanation offered for a small, so far unexplained subset of these events, not an established mechanism. What the Planck star and tunneling proposal actually offers isn't proof. It's a way to ask the original question without immediately running into Oerdely's wall. Not, can an eternal white hole exist in a universe full of matter? It cannot. That answer hasn't changed. The new question is narrower and stranger. Can a black hole, somewhere out there, be quietly finishing its life by briefly becoming the very thing physicists spent 40 years concluding was impossible to sustain? Nobody has confirmed that it does. Nobody has ruled it out either. There is one place in physics where something white hole-shaped is sitting in plain view, and it isn't hiding in a distant galaxy or a theoretical proposal about primordial black holes. It's underneath everything, at the very start of this universe's own history. Run time backward far enough, past the stars, past the first galaxies, past the point where matter and light stopped being tangled together, and you reach a boundary, a past singularity, a moment before which the equations of general relativity simply stop giving meaningful answers. Everything we can observe, every photon, every atom, every structure in the sky, emerged outward from that boundary and has been moving away from it ever since. Nothing before it is accessible. Nothing can fall back into it. Structurally, that description matches a white hole almost exactly, a region defined entirely by what comes out of it, with a horizon in time rather than in space, and a past nothing can reach back into. It's a strange thing to sit with, that the clearest candidate for something white hole-shaped in the whole universe might be the universe's own beginning. I find myself returning to this one more than any other part of the subject, because it reframes the entire search. We've spent this whole time asking whether white holes exist somewhere out there, scattered among the stars like black holes are. But if the comparison holds even loosely, we are not looking for a white hole. We are standing inside the aftermath of what might be the only one that ever worked. I want to be honest about how far that comparison can actually be pushed, because the temptation here is to treat it as settled, and it isn't. The structural resemblance between the Big Bang and a white hole's past singularity is a genuine and long-recognized one in cosmology. But recent theoretical work complicates it rather than confirming it. The cosmologist Enrique Gaztañaga, at the University of Portsmouth has spent several years developing a competing picture, culminating in a 2025 paper in Physical Review D, arguing that the early universe's expansion looks less like a clean white hole explosion outward from nothing, and more like the rebound of an enormous gravitational collapse. A black hole, in effect, that reached a maximum density and bounced. This is contested, active research, not a resolved question, and I'd rather tell you honestly that physicists disagree about it than pretend the comparison closes neatly. What doesn't stay open to debate is the instability problem, and it's worth carrying Erdely's argument all the way out to this scale before we're done with it. If even a wisp of ordinary matter is enough to collapse a small white hole into a black hole, then an early universe already dense with plasma, radiation, and the seeds of every structure that would later form should have applied exactly the same pressure at a much larger scale to any white hole-shaped process trying to unfold within it. The Big Bang, if it behaves like a white hole at all, did so inside conditions that Erdely's own reasoning says should have been hostile to the idea from the very first instant. That it may have happened anyway, if it did, doesn't overturn his result. It suggests that whatever occurred at the origin of this universe operated under physics we don't yet have, the same unfinished physics that governs the singularity itself, past the point where general relativity alone can still speak. There's a thread running through everything covered tonight, and by now it should be visible without my having to point at it directly. Every version of a white hole we've considered, the eternal Kruskal-Sekares one, the isolated primordial one, the momentary bounce from a collapsing star, survives only by being removed from contact with the rest of the universe. Perfect emptiness, a vacuum with nothing nearby, a birth so early that almost nothing existed yet to interfere with it. Over and over, the condition for a white hole to exist is the condition our universe has never actually offered anywhere, at any point in its history that we can observe. The rest of the universe is the one thing nothing gets to be removed from. You don't need to resolve any of this before you sleep tonight. Somewhere above, wherever you're lying right now, none of what we've covered has paused to wait for you to finish thinking about it. The stars that were already old when Schwarzschild wrote his letter from the front are still exactly as old as they were an hour ago. Whatever this universe's true beginning actually was, white hole or something we don't yet have a name for, it has already happened, completely, and nothing about tonight changes that. You can let it go. Here is what's actually true, after all of it. Somewhere in Einstein's equations, since 1916, there has been room for an object that only ever gives, never takes. A horizon that refuses everything trying to come in. For over a century, physicists have taken that idea seriously, drawn its complete geometry, tested its edges, and eventually watched it fail every single time they asked it to survive contact with a real universe. Not because the mathematics was flawed, because the one thing a white hole needs in order to last is the one thing this universe has never had enough of to offer. Nothing else around it. You have been lying there for the better part of an hour, maybe closer to sleep now than you were at the start, while a dead soldier's equation, a napkin sketch a colleague thought wasn't worth publishing, and a 40-year-old proof about blue-shifted starlight all quietly agreed on the same thing. That we have never seen a white hole is not a gap in our instruments. It may simply be what it looks like when an idea this pure meets a universe this crowded. The absence itself is the finding. If there is a place where something like this still happened, even briefly, It is behind us rather than ahead of us, somewhere in the first unmeasurable fraction of a second, when there was, for one instant, less to get in the way. Whether that counts as a white hole in the way Schwarzschild's equations meant it, nobody currently knows, and I suspect nobody will for a long time. There is a newer idea sitting just past all of this, one I haven't taken you into tonight. The possibility that black holes forming right now, somewhere in this universe, might already be quietly finishing that same journey in reverse, one Planck star at a time. That's a night on its own. For tonight, it's enough to hold this much. Every horizon we've talked about only ever does one of two things. It lets things in and keeps them, or it lets things out and can't keep anything at all. Nothing has ever been found that does both. Somewhere above the room you're in, there is light still leaving places it was never going to return to, indistinguishable, so far from all the ordinary light we've already learned to explain without needing this idea at all. Maybe that's all a white hole has ever really been, not a place, a kind of leaving. The sky keeps doing this whether or not you're watching. I'll watch it with you again next time. Sleep well.